Chapter 3, Power and Energy Potential Study. 3.1 Gross, Net, Operating and Design Head. 3.1.1 Energy Head Gross Head, H, in general, gross head, H, equals difference of water level in the head race and water level in tail race. For storage project, gross head, H, equals difference of water level in the reservoir and water level in tail race. For ROR project, gross head, H, equals difference of water level at the point of diversion and at the point where water is returned back to the river. For hydropower with Pelton turbine, gross head, H, equals difference of water level at intake and level of turbine axis. For hydropower with Francis turbine, gross head, H, equals difference of water level at intake and water level in tail race. Net head, H, the head available at the turbine after deducting the head losses within the system is called the net head. Operating headed is the difference of water surface elevation in the forebay and tail race after making due allowance of approach and exit velocity heads. Operating head equals total energy level at forebay/surge tank entrance, total energy level at exit. Rated headed is the head at which the turbine functioning at full gate opening will produce a power output equal to that specified in the nameplate of the turbine. Design headed is the net head under which the turbine reaches peak efficiency at synchronous speed. 36. Power potential, P. The total power potential for a head of H and a discharge of Q is P equals eta gamma QH. Hydraulic efficiency, eta H, it is the ratio of net head to the gross head. It represents the total losses from intake to powerhouse. Net head, H, equals gross head, H, asterisk hydraulic efficiency. Overall efficiency, eta O, it is the product of hydraulic efficiency, turbine efficiency and generator efficiency. Eta O equals eta H asterisk operator eta T asterisk operator eta G. Design discharge, the maximum discharge that is diverted from the source to meet the demand is known as design discharge. 3.1.2 Gross potential power estimation. We know that power production depends upon discharge and head. In order to determine the gross potential, a river basin is divided into several cascades. Based on the head and hydrograph of that particular cascade, the power can be calculated. These individual powers are summed up to find out total gross potential. Total power, P, equals N eta gamma QH. Where gamma equals specific weight of water, SI unit, Q equals discharge in cubic, H equals head in meter, N equals number of cascades. 3.2 Plant and installed capacity. 3.2.1 Plant capacity. It is the capacity of the plant with respect to available head, discharge and efficiency. Plant capacity may be selected either by running plant of the base portion to utilize maximum energy of flowing water or by running the power plant at the peak load period for better operational convenience and efficiency. 37. 3.2.2 Installed capacity. The maximum power which can be developed by all generators of the plant at the normal head and with full flow is called installed capacity. In other words, the economically viable plant capacity is called installed capacity. Thus, installed capacity equals eta gamma QDH, where QD equals design discharge. 3.3 Energy flow diagram, related to FDC, firm and secondary power and energy. This part has already been discussed in Chapter 2. However, once the installed capacity has been found out, the discharge above design discharge won't be usable. So energy above it will be spilled. The energy diagram is shown below. For ROR project, power equal to installed capacity is produced until design discharge is available in the river. Once the discharge begins to decrease, the corresponding power decreases and finally reached a firm value at lowest discharge. In case of storage project, water is stored to increase design discharge and corresponding capacity. The volume of storage can be found out by calculating area of deficit under flow duration curve. Figure 1, Power duration curve. 3.4 Economic consideration in HP system, marginal cost benefit approach and introduction to optimization approach. 38. 3.4.1 Determination of installed capacity of a hydropower plant. The installed capacity of a power project is determined using economic analysis. The basic two approaches are discussed below. Marginal cost-benefit approach. In this approach, installed capacity is determined by equating marginal cost with benefit. Marginal cost is the cost of production of one additional unit of power. Marginal benefit is the benefit obtained from that additional power. Let X% of duration correspond to the best installed capacity for 1 kilowatt generation. Figure 2, Marginal Cost-Benefit Approach. Variable cost equals cost of electromechanical installation, civil cost is not included. Life of plant equals n years. Interest rate equals I% per annum. Energy generated annually equals X% asterisk 1 kW asterisk 24 HR asterisk 365 equals 87.6 x kilowatt hour. Marginal benefit equals 8760 kilowatt hour asterisk energy rate. I, annual cost equals variable cost asterisk CRF, capital recovery factor, CRF equals 1 plus I, 1 plus I, minus 1 O and M equals certain percent of variable cost. Marginal cost equals annual cost plus O and M cost. 2. Thus, equating above two equations we get value of X that corresponds to best installed capacity. 39. Optimization approach. Power is the function of head and discharge. Increasing the percentile of available flow, design discharge decreases. For the low design discharge, the size of hydropower and hence its components will decrease. This will reduce the project cost. However, the power generation will also reduce, thus reducing the annual revenue. Thus, the discharge for different percentile time is calculated from flow duration curve and corresponding revenue and cost are calculated. The optimum capacity is fixed as the installed capacity. 3.5 Estimation of power and energy potential and its demand prediction methods. 3.5.1 Demand or load prediction. Demand is the need of energy that is requested by the customer in market, community, and region and in country. The power demand classified into A. Residential, B. Commercial, C. Industrial and D. Others. The power demand is generally depends upon population, living standard of population or society, climate, purpose of using power, general costume, and culture. Short-term prediction, covering a period of 4 to 5 years. It is done mainly for designing operation plans identifying the areas of deficit and surplus power. Medium-term prediction, covering a period of 8 to 10 years. It is done for formulation of expansion program of power generation and transmission facilities. Long-term prediction, covering a period of more than 20 years or more. It is done mainly for formulation of country's prospective plan for power generation, country's power resources and mode of transmission and its voltages. Short-term prediction is more significantly influenced by the present environment. The economic factors and prospective plans has significant role for long-term forecasting. 3.5.2 Method of load or demand prediction. Depending upon the data availability, degree of accuracy required, prevailing circumstances, the following methods of load forecasting are generally used. 40. Class-wise consumption. The historical class-wise power consumption data in sector like residential, commercial, industrial and others are used for analyses to find the need of power in future years based on the individual class-wise growth rate and coming implementation plan. Data lacking is a major problem in Nepal and hence rarely used for forecasting. Historical trends. In the case of lacking class-wise data, power demand, the total power demand and consumption are used to have trend analyses in the past. The past trend is used to forecast demand for future. The historical trend may not be valid for future as the trend line of demand rapidly changes with the development of technologies and socio-economic activities. Correlation between power consumption and economic development. The correlation analyses between the power development and economic development GDP have shown that there is a good correlation between them. The data of GDP and per capita energy consumption of the same nation or international country to find the relationship between the economic development and the per capita energy demand. The relation is used to compute the energy demand for the targeted economic development. GDP measures the economic condition within a country population. GDP depends on number of household, index of industrial production, summer days, cold days, oil price and electricity price. So these data are important for selecting the economic development data of other countries. Mathematical formulae. The mathematical formulae can be developed based on analyses of observed data resulting empirical formula. Incremental rate formula P equals PO, 1 plus or slash 100, and where P power demand after n years PO power demand at present are incremental rate of power demand in percent. For Nepal the incremental rate of power demand is about 9% 10%. Country-specific formula Belgium formula E equals K asterisk M degree 6 asterisk 20 for 65 asterisk T where 41. Electricity consumption TTH years M index of manufacture production varies for nation to nation T time T to which consumption is to be projected K adjustment factor also varies from nation to nation depending upon the electricity consumption and economic activities. Shear formula log 10 G equals C 0.15 log 10 U or G equals dot. Where G annual growth in generation / demand in percent U per capita generation or demand C constant equals 0.02 asterisk population growth rate percent plus 1.33. 3.6 load curve, mean and peak load, load factor, utilization and diversity factors. 3.6.1 load curve. It is a graphical representation of power consumption with respect to any time. A load curve may be daily, weekly, monthly, or annual load curve. Area under load curve of particular duration gives the total energy consumption in that duration. A typical load curve is shown below. Figure 3, load curve. 42. 3.6.2 maximum demand. The highest instantaneous value of the demand is known as the peak load or peak demand. Generally, peak load is defined as that part of the load carried at intensity greater than 4/3 times the mean load intensity. 3.6.3 demand factor. The ratio of actual maximum demand on the system to the total rated load connected to the system is called the demand factor. It is always less than unity. Demand factor equals 3.6.4 average load. The average load or average demand on the power station is the average of load occurring at the various events. It can also be stated as energy delivered in a given period divided by the number of hours in that period. Depending upon the duration of time period such as a day, a month, or a year we get daily, monthly or annual average load. Daily average load equals monthly average load equals annual average load equals 3.6.5 load factor. It is the ratio of the average load during a certain period to the maximum or peak load during that period. The load factor is thus related to the certain period of time consideration and therefore, there will be daily load factor, weekly load factor, monthly load factor and yearly load factor depending upon the time period. Load factor, LF, equals. Load factor of a power plant that has been used to supply the power in a system would vary greatly with the character of the load. High load factor in industrial area is nearly 1 while it is low in residential area as low as 0.25 to 0.30. The installed capacity of a power plant /S has to be equal to the peak load, but the total number of units kilowatt-hour generated or used will be governed by the average load. If load factor 43 of a power plant is low, large proportion of the generating capacity remain ideal for most of the time and the cost of generation per unit energy, kilowatt-hour, or power is high. Load factor value of 0.80 is generally taken during the feasibility study of hydropower project in Nepal. 3.6.6 utilization factor or plant use factor. It is the ratio of peak load developed during a certain period to the installed capacity of the plant. Utilization factor, UF, equals it represents the maximum proportion of the installed capacity utilized during that period of consideration. With constant head commonly in hydropower plant, utilization factor would represent the ratio of the water actually utilized for peak load power supply corresponding to the maximum water that can be withdrawn from the river to produce installed capacity. The values of utilization factor commonly vary from 0.4 to 0.9 depending upon the plant capacity, load factor, and available poundage or storage. 3.6.7 capacity factor or plant factor. It is defined as the ratio of the energy that the plant actually produced during any period to the energy that it might have produced if operated at full capacity throughout the period. Capacity factor, CF, equals. The capacity factor will be equal to the load factor if the maximum peak load of the duration is equal to the installed capacity of the power plant. For hydropower plants, the capacity factors varies from about 0.25 to 0.75 depending upon the plant capacity, available poundage or storage and the load characteristics curve. 3.6.8 Diversity factor. It is the ratio of sum of all individual maximum demands by the customer to the actual peak load of a system. Diversity factor, DF, equals it gives the time diversification of the load and used to decide the sufficient generating plants and transmission utilities. If all demands came at the same time, the diversity factor will be 44. Unity or 1. The installed capacity that needed to be installed in the power system would be much more. But the diversity factor is generally much higher than unity. 3.6.9 Reserve factor. It is the reciprocal of utilization factor. It is the ratio of installed capacity to the peak load. Reserve factor equals relationship between capacity factor, load factor, and utilization factor. Capacity factor equals load factor x utilization factor and reserve factor equals load factor / capacity factor. Proof: CF equals LFX/UF from RHS. LFX/UF equals average load / peak load x peak load / installed capacity equals average load / installed capacity equals CF. So CF equals LFX/UF and 1/UF equals LF/CF equals RF. 3.7 Power demand variation, daily, weekly, monthly and annual variation of power. 3.7.1 Daily load curve. Daily variation of power supply or demand in a power system is known as daily load curve. The power demand is not constant in different hours of a day and it varies from hours to hours depending on the types of areas that have to be served. For domestic area, the peak demand generally occurs at 18 to 2000 hours for cooking and lighting purpose at evening. The peak demand time slightly shifted earlier during winter season and the peak demand is also higher than that in summer season. The daily load curve for industrial area is quite different than that of the residential as the peak load generally occurs in daytime as the industries runs at full phase during the office working hours. The peak load may not alter too much even in nighttime if there are large numbers of industries that runs continuously 24 hours. Figure 4, typical daily load curve for residential area. 45. Figure 5, typical daily load curve for industrial/commercial area. 3.7.2 Weekly load curve. The power demand or consumption in a community or society is not same in all days of a week. The variations of the load in different days of a week are known as weekly load curve. Figure 6, typical weekly load curve for industrial/commercial and domestic area. 3.7.3 Seasonal load curve. The curve showing the variation of power consumption or demand in a power system feeding to a community/society or cities in different seasons is known as seasonal load curve. The seasonal load of a particular place is mainly governed by the climate and culture besides the living standard and style of the society. For example, the power demand in the winter in Himalayan and high mountain areas are higher than that in the Terai/plain terrain region of Nepal mainly due to cold and arid climate in the winter season. The power demand in the September and October is high in Nepalese society mainly due to main festival, Dashain and Tihar. The industries and commercial sectors are also run at full phase targeting the supply and service for the main festival. 46. The study of the power/load variation is important for planning of power production/generation and transmission and distribution utilities. It also helps to impose systematic tariff of electricity based on the consumption amount and the sector of services. It also helps to prepare guidelines for operation and maintenance of power projects to achieve the targeted service at optimum cost for generation, transmission, and distribution system. Hence, it ultimately helps to formulate policies in energy sectors to support sustainable economic development of country. 3.8 Power grid, introduction and components of power grid system. Generating stations, transmission lines, and the distribution systems are the main components of power system. Since most of the hydropower stations are situated far away from the load centers, it becomes necessary to transmit bulk power from such remote areas economically. The efficiency of transmission is quite high when the power is transmitted at a high voltage. Power grid is an essential component of the power system and it is dedicated to evacuate power from the generation point to the nearby load center and then distribute to the end customer. Grid line generally transmit high voltage of 33 to 400 kV or higher. The power grid can be separated into two parts: 1, transmission lines, and 2, distribution system. Based on the number of production units connected to the grid, it can be classified into isolated and integrated grid. In isolated grid, the power to the grid is supplied from only one power station, while in integrated grid the power is supplied from two or more than two power stations. In grid system, the general planning is such that some station may be run as baseload station while some other may be run as peak load stations. Power production is designed for optimizing the cost and comprising mixture of thermal, hydro and nuclear sources. 3.8.1 Advantages of integrated grid over the isolated grid: increase reliability. In the event of a forced or planned outage of a power station, the affected system can be fed from other stations. River flow, storage facilities, floods and drafts are the factors that may affect the hydropower generation. Reduction in the total capacity. In an isolated system, reserve units must be maintained separately in power station, but the reduction in total installed capacity depends on the characteristics of interconnected system and desired degree of service reliability. 47. Economic operation. Power station might be far from the load center depending upon the natural resources available, e.g. thermal station can be built close to the source fuels, coal, mines, and petroleum refineries. 3.8.2 Components of power system. Generators. Generators are machines which generate electrical power when rotated about by external sources of power such as water, steam, etc. Generators of hydropower stations have a speed range of 70-1000 rpm. The generators can have either a vertical shaft alignment or a horizontal shaft alignment. Transformers. These are devices which increase or decrease the voltages. It consists of a core made from laminated silicon alloy steel having 0.35 mm to 0.50 mm thick, each layer being insulated by thin paper or varnish. Two coils of insulated copper wire known as the primary and secondary coils are wound around the core. A voltage in the primary coil produces a magnetic field in the core and induces voltage in the secondary coils. The generation voltage of a hydrogenerators may vary from 6 kV to about 20 kV. Whereas the transmission voltage in case of long transmission line losses can be minimized, and a transformer has to be provided for stepping up the generator voltage to transmission voltage. Switchgear. The powerhouses are designed to give continuous service without interruption of power. But sometimes faults may develop in the system due to man-made or natural causes. In such cases, suitable protective devices have to be provided to locate the faults, isolate the faulty circuits from the system, and to clear the faults as quickly as possible. The switching and protective equipment used for this purpose is known as switchgear. It consists of circuit breakers, relays, and equipment for controlling and measuring such as current and potential transformers, isolators, lightning arresters, control panels, switches and fuses, etc. Substations. It is generally located just outside the power station building on the ground or sometimes on the RCC roof of the powerhouse. It consists of incoming line, outgoing line, bus bars, transformer, high and low voltage switchgear like circuit breakers, isolators and lightning arresters, metering panels, dropout fuses, station earthing system, etc. 48. Control room equipment. It consists of switches to control the operation of units, recording and signaling equipment, and instruments measuring or controlling voltages, currents and frequencies of generation, outgoing feeders, auxiliary power consumption and battery charging equipment. Telemetering and telephone equipment and reservoir and tail race water level indicators are also included in control room. Figure 7, Power Grid System of Nepal Panati. Balaju, Substation. Distribution to consumers.